So this is lesson 3, and in this lesson we're going to be looking at the rate equation and how it's determined empirically. So let's do an experiment with so we're doing it with HCl and sodium thiosulfate. So we'll change the concentrations of those, and again we'll do a series of experiments here. And then for each of those we'll measure the rate of the reaction. This is all in the topic booklet, obviously. So I could start off with a couple of concentrations of HCl and sodium thiosulfate. For my second experiment, I'm going to keep the concentration of HCl the same, but I'm going to double the concentration of sodium thiosulfate, and we'll see how that affects the rate. So in the first experiment, my rate is 4.8 times 10 to the minus 3, and in my second experiment, my rate is 9.6 times 10 to the minus 3. So if I look at what's happened here and look at what's happened here, here the concentration has doubled, and here the rate has doubled. In other words, the relationship between rate and sodium thiosulfate is first order. So when I start to construct my rate equation, I know that there's a first order relationship between sodium thiosulfate and rate. Because this doubles, that doubles, this quadruples, that will quadruple. Everything I do to this has exactly the same effect on that. Okay, so now let's do another set of experiments. This time we'll double the concentration of the HCl. I'll keep sodium thiosulfate at 0.2, and now again the rate is 9.6 times 10 to the minus 3. What's happened here? So that has gone up by 2, and this, no change. So what does that tell me? That tells me that doubling the concentration of HCl had no effect on the rate. So in other words, that must be zero order. Let's do another example. Let's get away from thiosulfate. Let's imagine I've got some reaction where A and B go to make C and D, and we're going to do the same thing again. We're going to change the concentration of A, change the concentration of B, and look at how that affects rate. So let's start off with, again, this is just from the book. Concentration of A is 0.04, concentration of B is 0.05, the rate is 1.6 times 10 to the minus 3. Second experiment, I'm going to go for 0.06 from A, and I'm going to keep B the same, and my rate has gone up to 2.4 times 10 to the minus 3. So again, if we look at what's happened here, that's gone up now by 1.5. The rate has gone up by 1.5 as well. So that would enable me to say that A must be first order, because the change in A is copied in the rate. For my third experiment, I'm going to go to 0.08 for A and 0.1 for B, and now my rate is 12.8 times 10 to the, I think it's supposed to be minus 3. Yes, it is. The deviation from standard form here, it's quite common in these tables. It's to enable us to compare these numbers more easily. It's easier to compare 12.8 to 1.6 than it is to compare 1.28 times 10 to the minus 4 with 1.6 times 10 to the minus 3. I meant times 10 to the minus 2, didn't I? Anyway, you get me. Right. What's going on with B? Okay, well, if we look at if we go compare experiment 1 and experiment 3, what's changed from experiment 1 to experiment 3 with A? Well, it's doubled. So what's happened between 1.6 and 12.8? Well, it must have at least doubled because we know A is first order. So some of that change must be accounted for by the change in A. Well, 1.6 doubled is 3.2. So let's sort of keep that as a tally. It would be 3.2 at the moment. But we've also changed B. And B has also doubled. So what effect has doubling B had on the rate? Well, we do expect the rate to be 3.2 times 10 to the minus 3, just as a result of doubling A. But on top of that, it's gone up to 12.8. Well, what's the difference there? Well, that's times 4. 3.2 times 4 is 12.8. In other words, doubling B has increased the rate by a factor of 4. Well, if doubling something has increased the rate by 4, that means it's second order, because second order is B squared. 2 squared is 4. So rate must be A to the 1, or you could just write A, and then concentration of B squared. And that's our rate equation right there.